Continuing with our examples where we're trying to sketch the graph of the function, let's look at the function f of x defined by x divided by x squared plus 1. First thing we should look at is the domain, and here the only place where we may have a problem is if we divide by 0, but the bottom x squared plus 1 is at least 1. It is 1 plus a square, and the square is positive. So in particular it doesn't take the value 0, and therefore the domain is all the reals. Similarly, for the same reason, the limit of the function is never infinite at a finite value, and therefore there is no vertical asymptote. Still looking for asymptotes, if we look for the limit of f when x goes to infinity, we have a quotient of two polynomials, and we have the highest degree at the bottom. So we have seen that in that case the limit of the function at infinity is going to be 0. And that means that the horizontal line y equals 0, in other words the x-axis, is an asymptote. Now that we have found the asymptotes, we want to look for the intervals of increase and decrease of the function, and we know that that depends on the sign of the first derivative. So we calculate the first derivative using the quotient rule to differentiate. We get the derivative of the top, that's derivative of x, we get 1, multiplied by the bottom unchanged, x squared plus 1, minus the derivative of the bottom, that's 2x, multiplied by the top unchanged, which is x, all this over the square of the bottom. After simplification, we get x squared plus 1 minus 2x squared, in other words 1 minus x squared at the top, and that factors further as 1 minus x, 1 plus x. All this is over the square of x squared plus 1. Since we're interested in the sign of f prime, you see that the bottom is not going to influence the sign of f prime because it's always positive. So f prime is of the sign of the product 1 minus x, 1 plus x. So this is what we're going to put in our table. 1 minus x and 1 plus x, and f prime is going to have the sign of the product. The changes of sign are going to be either at negative 1 or 1. 1 minus x is positive if x is less than 1, that is, it's going to be positive on the left of 1. It is 0 at 1 and negative if x is greater than 1. 1 plus x on the other end is positive if x is greater than negative 1, that is, on the right of negative 1. It is 0 at negative 1 and negative for x less than negative 1. That means that on the interval negative infinity, negative 1, or on the interval 1 infinity, f prime is a product of a positive number with a negative number, and therefore f prime is negative. It is 0 at negative 1 and 1, since one of the factors at the top is 0 at these two values. And it is positive between negative 1 and 1 because both factors are positive. In terms of increase and decrease, that means that the function is decreasing on the interval negative infinity, negative 1, and also on the interval 1 infinity. It is increasing on the interval negative 1, 1. That gives us a local minimum at x equal negative 1, and this minimum value is f of negative 1. If you plug negative 1 in the original function, you get negative 1 at the top, negative 1 squared, which is 1, plus 1, so 2 at the bottom, in other words, negative 1 half. We have a local maximum at x equal 1, and this maximum value is f of 1, which is 1 half. So I'm going to put these values in my chart. And now, before we can sketch the graph, we need to find the intervals of concavity of the function, where it's concave up or concave down, and the inflection points. Before I turn to that, I'm just putting in the chart the fact that the limit of the function is 0 at plus or minus infinity, in other words that y equals 0 is an asymptote. To calculate the second derivative, I'm using again the quotient rule because I'm differentiating 1 minus x squared divided by x squared plus 1 squared. So I get derivative of the top, that is negative 2x, multiplied by the bottom unchanged, x squared plus 1 squared. Then I subtract the derivative of the bottom. The bottom is x squared plus 1 squared, so it's a square of a function. To differentiate it, I use the chain rule. I get 2x squared plus 1 multiplied by 2x. And then I have to multiply this derivative by the top unchanged, which is 1 minus x squared. All this is divided by the square of the bottom. Since the bottom was already x squared plus 1 squared, its square is x squared plus 1 to the fourth. Now we want to simplify that because we're interested in the sign of the second derivative. You can see that we have a sum of two terms, and in each one of them we can factor out negative 2x and also x squared plus 1. So this is what I'm going to do. If I factor out negative 2x times x squared plus 1, in the first term it's multiplied by x squared plus 1 because I have x squared plus 1 squared. In the second term, if I take out negative 2x and x squared plus 1, what remains is 2 times 1 minus x squared. Multiplying things through, in the last parenthesis at the top I get x squared plus 1 plus 2 minus 2x squared. In other words, 3 minus x squared. I'm sorry, yes. And so I have 3 minus x squared in that parenthesis. I can get rid of the negative sign in front of the fraction and I get 2x multiplied by x squared minus 3. So this is what we have for the second derivative. X squared minus 3 factors further as x minus root 3, x plus root 3. So now we're interested in the sign of the second derivative, and we have it in factored form where we can analyze its sign by analyzing the sign of each factor individually. You see that the bottom is the cube of x squared plus 1, and x squared plus 1 is always positive. So this bottom part is not going to influence the sign of the second derivative. It only depends on the sign of the three factors at the top. So I'm going to put them in my chart. 2x is going to change sign as 0, x minus root 3 at root 3, and x plus root 3 at negative root 3. So this is where I may have changes of sign. 2x is positive if x is positive, 0 at 0, and negative for x negative. X minus root 3 is positive if x is greater than root 3, it is 0 at root 3, and it is negative for x less than root 3. X plus root 3 is positive if x is greater than negative root 3, that is on the right of negative root 3. It is 0 at negative root 3 and negative for x less than negative root 3. That means that the second derivative, which is a product of the same sign as the product of these three factors, when x is between negative infinity and negative root 3, all three factors are negative, so the second derivative is negative, product of an odd number of negative factors. Between negative root 3 and 0, I have two negative factors, one positive factor, so the product is positive. Between 0 and root 3, I have one negative factor, an odd number of negative factors, so I have a negative product. And if x is greater than root 3, all three factors are positive, so the product is as well. If we interpret that in terms of concavity, when the second derivative is negative, the function is concave down. When the second derivative is positive, the function is concave up. So we get this type of concavity. You see that we have three changes of concavity and the function is defined on the real line. So these three changes of concavity correspond to three inflection points. We have one at x equal negative root 3. The second coordinate is at negative root 3 over 4. This is what we get by plugging negative root 3 in the original function. We have an inflection point at 0, and if we plug x equals 0 in the function we get 0, so 0, 0 is an inflection point. And when x is root 3, if I plug that in the function I get root 3 over 4. So this point root 3 over 4 is also an inflection point. I'm going to enter these coordinates in my table to have all the information I need in the table, and turn to the question of sketching the graph from the information we've found. We should start with asymptotes. In this case there was no vertical asymptote, no slant asymptote, and only an horizontal asymptote, namely y equals 0. Then we should plot the important points, which are the local extrema and the inflection points. We have two local extrema. We have a local minimum of coordinates -1, -1/2, where we have an horizontal tangent because the derivative is 0, and a local maximum at 1, 1/2 with again an horizontal tangent. We have 3 inflection points, one at negative root 3, negative root 3 over 4, one at 0, 0, and one at root 3 over 4. Now we need to connect these points with the information we have. On the interval negative infinity, negative root 3, when x goes to negative infinity, the function gets close to 0. And on that interval, the function is decreasing and concave down. So we obtain something like that, decreasing, concave down, approaching the x-axis when we go towards negative infinity. On the interval from negative root 3 to negative 1, the function is still decreasing, but now concave up. So we obtain a piece of graph, an arc that is decreasing concave up that joins this inflection point with the local minimum. On the interval from negative 1 to 0, the function is still concave up, but this time increasing. So I'm going to connect my minimum with the next inflection point with a smooth arc that is increasing and concave up. From 0 to 1, the function is still increasing, but now concave down. So I'm going to connect my inflection point at 0, 0 to the local maximum at 1, 1/2 with a smooth arc that is increasing but concave down. From 1 to root 3, the function is now decreasing and still concave down. So I connect the local maximum with the next inflection point with a smooth arc that is decreasing, concave down. And finally, for x greater than root 3, the function is decreasing but concave up, and when x goes to infinity, f of x should approach the x-axis. So we get something, a smooth arc that is decreasing, concave down, going towards the horizontal asymptote of the x-axis. So this is what the graph looks like. On this particular graph, we don't really see the behavior for x very large or very negative large. So if we zoom out, there is what we would see, and you see that indeed the values of f of x level off to 0 when x gets large or negative large. Now let's turn to the next video to see a few more examples.